All right, what if I am given a sloped surface, and this surface is at 35 degrees, and I'm going to put my 100 kilogram block on here, 100 kilograms, and I'm going to apply a force P that is acting horizontal to the surface. And let's see, my coefficient of friction this time is 0.25. All right, I wish to find P to maintain equilibrium. Okay, now that's very specifically worded, because if you think about this block, I have two options. If my P is small enough, the block will slide down. If the P is large enough, the block will slide up. So we actually are going to have a range of values to keep the block from sliding down and low enough to keep from pushing the block up. Okay, so maintain equilibrium, keep it where it is. So it's not letting it slide down and not letting it move up. So my solution is going to start with keep it from slipping down. All right, so in this case, I've got my block. That has a weight of 100 kilograms times gravity. I have P here that I'm looking for, and if we're keeping it from slipping down, which way is the friction acting? Friction will be pushing up, right, if it wants to move down. And then I will have my normal force, which is acting perpendicular to the surface, which in this case is 35 degrees. So if I'm drawing some angles here, this angle here is 35 degrees, which means perpendicular to it would be this vertical angle, 35 degrees. All right, I'm going to do it by setting X horizontal and Y vertical. Either way, we have simultaneous equations. So summing for my force in the Y direction, I am going to have minus 100 kilograms times gravity, 9.81, plus the normal force, cosine of 35 degrees, and then plus my friction force, sine of 35 degrees. Now we are trying to keep it from slipping down, which means we are just on the cusp of movement downwards, which means my friction is going to be friction max, because we're about to move down. Moving can be either way, okay? So this is gravity is pulling it down. We're about to start moving. So this is mu s n. Okay, so now I'm down to one unknown because my mu s is equal to 0.25. And we find that the normal force is equal to 1019.2 newtons. And then I can sum for forces in the x direction. And I will have P plus my friction force, cosine of 35 degrees, minus my normal force, sine of 35 degrees. And that's it, that's acting in the x direction. So this value goes in here, the 1019, and my friction force again goes to 0.25 times my normal force, which is 1019.2 newtons. and I find that my P down, okay, or my minimum required force, right, to keep it from slipping down, the minimum effort that I need to keep it from moving down is equal to 376 newtons and 3 significant digits. Okay, so that keeps it from slipping down. That's the minimum amount of effort if I'm helping my friend move a really heavy box up the ramp into the truck, right? If I just keep it from slipping down, minimum amount of effort. Okay, now let's go to maximum amount of effort, which is helping my friend push the box up into the truck. So just before moving up the ramp or the sloped surface, okay, what changes here? Does the weight of the block change? Nope, it is still 100 kilograms times gravity, okay? We are still pushing horizontally here, but now we're trying to push it up the slope, which means friction again is working against us, right? So it's pushing down, and it's max because we want it just before movement. That's the maximum amount that we push just before it starts to move. Okay, and then our normal force is still acting perpendicular to the surface. All right, doing the exact same set of equations, but just moving direction of friction. Okay, normal will always act pushing up. Okay, the ground is always going to be pushing up on the box, but friction is going to be acting against movement. Okay, so summing forces in the y direction, I have 100 kilograms times gravity, and I didn't write out all my angles. This is still 35 from the horizontal, and this is still 35 from the vertical. So we are going to be minus my friction force, sine of 35 degrees, and then plus my normal force, cosine of 35 degrees, and my friction force is still that maximum, friction max, which is equal to mu Sn, okay, where that is 0.25 normal force. Solving for that normal force, I get 1,451.7 newtons. Okay. Larger normal force because we're pushing on it more to start scooting it up because that friction is acting against us. And then I sum forces in the x direction. And that's going to equal P minus friction cosine of 35 degrees minus my normal force, sine of 35 degrees. Okay, normal force, this number replaces this. Friction becomes 0.25 in the normal force, which is again that value. Do you like my arrows? And I end up with P up equal to 1,130 newtons. So to maintain equilibrium, I need to push somewhere between 376 newtons and 1130 newtons. Okay, and I could put equal signs there. Somewhere between that to keep the block from moving anywhere.